He's wrong. Although if you're playing 3/5, clerics are OP. Okay. It's AP time. It's AP time. If you're taking AP next year and you stick around, it's like I'm teaching you it before you're even in class. That means next year is just like a review. Okay, the question I'd like to talk about a little bit has to do with big old Bernoulli. Remember, with big old Bernoulli, we have this giant equation. Let's see if I can fit it all. P1 plus rho g, and we are using y1 this year. I normally use h1, but whatever. Plus 1/2 rho v1 squared equals p2 plus rho g y2 plus 1/2 rho v2 squared. Whew! Whew! So for big old Bernoulli, not big old Bronoli, we've got this giant equation which is essentially relating pressures of the sides of some tube. It's looking at work done due to height differences in that tube, and it's all being related to the kinetic energies as well. We know that for fast-moving fluids, the pressure around those regions decreases. We see this not only in things like Venturi tubes, but we also see them in hurricanes whenever you have very low pressures in the eye of the storm. Tornadoes, you'll see some of this as well. Interestingly enough, you'll actually see this if you have a side burner on a propane grill at your house. Whenever they go to attach the side burner, they use a Venturi tube in order to, as they're pushing the propane gas down the line, they don't do a direct attachment, they do a floating attachment. And because of that, they leave a little opening gap in the side to pull in more airflow so that they can get a good flame to exist. So kind of a weird, use of that, but a logical use of that nonetheless. What we're going to look at with Bernoulli's equation tonight, though, is in honor of the grandfather, my mother's side, we are going to be looking at the Martin-Martinac plane problem, where we take a Cessna 172 Skyhawk and we get it to fly. And we kind of prove why it could fly and how that would all work. So this is what we're going to look at. My grandfather Martin used to fly a Cessna 172 Skyhawk in his spare time for fun. If the Cessna has a wingspan area, as reported, just found online, of 16.2 meters squared, then what is the speed across the topside airfoil such that it could support 4 passengers for a total weight, including the plane, of approximately 1,100 kilograms, assuming that the plane is cruising at a velocity of 239 kilometers per hour across the bottom airfoil, which is traditionally the airspeed here. So if we want to kind of do this problem, we know that an airfoil has a low pressure and high pressure, and it's this low and high pressure that generates a pressure gradient up on the wing, and that pressure gives us a force divided by an area. So that's actually what's causing the plane to get some lift. This pressure multiplied by an area gives it a force. That force is the lift, and that's what's keeping our plane up. Okay. Now what we're doing in this problem is we know a few things. We know the mass of our Cessna is 1,100 kilograms. We know that the cross-sectional area of the Cessna is 16.2 meters squared. And we know that the velocity running across the bottom side airfoil, we'll call that region 2, and we'll call the upper region 1 with the low pressure. we know the bottom side air velocity is 239 kilometers per hour. And if we put that into some reasonable units, because let's get real, that is 66 approximately meters per second. Okay. Now, and if you're thinking back to last year, like, oh man, I missed last year. Last year was so much fun with F equals ma. Or if you're one of my CP students and we're learning about F equals ma right now, and you just found your way into this, what we actually have here is, if we look at the Cessna has a weight going down equal to the mass times gravity. And we know the mass. We know the mass here is 1,100 kilograms times gravity, 9.8. Might as well just call it 10. But that weight here needs to be equivalent to the force we're getting from the lift. It has to be. That's just how the plane is staying up. So we can actually say here is that the force from the lift is equal to the weight of the Cessna, which is equal to the 1,100 times 9.8. They have to be the same in order to keep a level cruising altitude. Okay. If we take a look at this equation with pressure, force, and area, because we know that this pressure gradient here, this change in pressure between the high and low regions of the plane, that pressure gradient, that delta P, has to give us a force of the lift divided by some area, which, if the force of the lift is equal to mg, that's 1,100 times 9.8, all divided by some cross-sectional area. So that's what we kind of just know right off the bat. So if we kind of know this, we have a free body diagram, we know some information about this. If we want to get this delta P, what we're actually looking for with this delta P here is we're looking for what is the pressure of region 2 minus the pressure of region 1. That's what we care about. What is that pressure gradient? Because if we have a pressure greater in 2 than 1, some positive pressure, we can assume up is positive, we'll get that lift. So if we want to go ahead and kind of solve this, we can use Bernoulli's equation. Bernoulli's equation has P2 and P1 in it. And if we look at this equation, what we can actually get away with here is these plane wings, you know, they have some thickness to them, but it's not like 30 feet high, it's not a mile high. What we can actually say is that this height here, delta H or delta Y, who cares? It's negligible, okay? It's basically the same. And because of that, let's just wipe these out. Oh, but you know, the 16 inches, that's the difference there. That could mean life. No, sure. It's essentially nothing. There's not enough difference in air pressure between a foot column of air to make a difference here. So let's just wipe it out of the problem, make our life a little easier. Now that we have P2 and P1, we can kind of set this equation up, and we have velocity and velocity, we can set this equation up. So setting this equation up for that can kind of give us what we are looking for. If we wanted to kind of write this out for completeness, we could say that P2 minus P1, that side of the Bernoulli, equals 1/2 rho times V1 squared minus V2 squared. Where remember, we are calling V1 the top side, and that's the fast. We're calling V2 the bottom, the slow side. So if we have this here and we kind of wanted to solve it, we could. I'm just going to call this delta P again. So if we take 2 delta P over the density, that's going to have to equal V1 squared minus V2 squared. And if we wanted to solve just for V1 here, we could. An important thing to recognize is that we're going to have to do a substitution back for this delta P. We have it up here earlier. Delta P is right here. So that's nice. Then we can just kind of solve this problem out. I'll let you kind of work through that math right there. We'll see a solution to this tomorrow. But with this right here, you should have a pretty good setup on how to go about this problem, looking at Bernoulli's equation and looking for differences in pressures. We're using the old pressure equation, we're using bigger old Bernoulli rewritten here, and then just kind of solving with a little bit of math. What you should be a little bit careful with is whenever you solve this, when you take the square root in order to solve for V1, you need to be careful. Okay, I'll just say that. You need to be careful when taking that. There's kind of a method of which to go through that. But if you go through it, you should be fine there. That problem's really over for you setting up a Bernoulli equation. Okay?